Hello maths fans, I am back with my favourite laureate. It is Martin Hare. This is going to be the third time, I think, that we have had an interesting discussion about all of the incredible things happening in Martin's head. So for those of you who possibly are new to the channel or are new to Martin and his amazing work, so you awarded the Fields Medal in 2014?
That's right.
Yes, which is one of the biggest prizes you can receive, and certainly I would say the biggest prize you can receive as a mathematician under 40. So I think Martin is awesome. We love Martin over here. So going back 5 years ago, we were talking also in Heidelberg, where we are now, and you mentioned the stuff you were thinking about could be veering towards Yang-Mills in quantum field theory. Is that still what you're doing?
Yeah, to some extent. So I mean, we had with several co-authors, we published 2 works in the meantime, in which go towards the building of a Yang-Mills theory in 3 dimensions.
Okay. Yeah.
And of course, the big $1 million problem is 4 dimensions. That's a completely different ballpark. So it's much harder.
Okay. Yeah.
So we're doing the easier stuff, but even in 3 dimensions, it's not really known. And we want to build this. You know, we built some of these dynamics, so some of these stochastic PDEs. They're like random evolutions of some random fields.
Yep.
And they have the property that if you sort of follow them along for a long time, then at very large times, they should kind of settle down to the theory you want to construct. So, right, like in a nutshell.
Yes.
That's kind of the idea. And so what we have is now a relatively good local solution theory for that process that we constructed.
So when you say local, are we talking local in space, local in time?
We're talking about local in time.
Okay.
In some sense, also local in space. So we have to restrict ourselves to like a finite region of space. So we cannot do that in like infinitely extended space. Yeah.
Okay. And what would a local solution, a local problem of this type look like? So I know, I mean, I'm hinting, can we talk about also visualizations? So to go back to the Tetris game that we've played before, I said the one where Martin pressed go and an infinite Tetris happened on the screen and created all these beautiful patterns. So is it sort of like, or analogous to, zooming in on one of those parts of the interface versus zooming out? Or is that not quite the right locality?
It's more about what could happen, but doesn't actually. So you imagine, so I can look at this visualization. Yeah. So here, this is some kind of a random string that wiggles around in some way on a sphere.
Yep.
You should really think of this as being thousands of little beads with little, springs that connect them together.
Okay.
And they're all having some kind of random force that kicks them around, but they're kind of kept together by these springs.
Yes.
And then they do this sort of wiggly motion. And here you see it moves pretty fast, but it behaves in a somewhat reasonable way, in the sense that it keeps quite cohesive.
Yep.
You could imagine what doesn't happen here, but you could imagine that, for example, one bit starts turning around on the sphere and then starts turning around on the sphere faster and faster, and this whole thing would sort of stretch until it reaches a point where it wants to kind of rip apart.
I see.
Right?
Yes.
So something like that could happen.
Yep.
And when you build solution theories for these kind of equations, you always get a solution theory up to the point where something dramatic like that happens, right?
I see.
And then you would want to prove that it actually doesn't happen, right? So I don't have a visualization of this happening because it doesn't happen.
Right. But that's good.
But that's good.
Yes, okay.
But you want to prove that it doesn't happen. And
Okay.
so that might be difficult to prove.
Yes, how do you even go about that? Before we hear more from Martin about the difficulty of solving a literal $1 million problem in the form of the Yang-Mills mass gap hypothesis, I want to just take a moment to focus on a problem a little closer to home. securing your personal data. Whilst most of us are now aware of the importance of maintaining privacy when online, I recently undertook a mass unsubscription from various mailing lists, for example. Such actions will only affect the collection of any new data. Any previous information you have entered online will still be available. This data is then harvested by data brokers who sell your personal information to the highest bidder. That could be your address, your phone number, your property records, or even information about your family members. But not to worry, this is where today's sponsor, DeleteMe, can help. I entered a few key details into their online system, and within 7 days I had a full privacy report listing all of my information currently being held by more than 50 data brokers. And most importantly, I also received information on the removal process being carried out by the privacy experts at DeleteMe. But it doesn't just stop there. DeleteMe continues to monitor sites and repeats removal of your data as and when it's needed. With a single-minded focus on the removal of personally identifiable information online, DeleteMe has only one focus: to remove customers' information from search results. If this sounds like something you'd like taken care of, then head to joindeleteme.com/TomRocks and enter the code TOMROCKS at the checkout for 20% off all DeleteMe consumer plans. You can also scan the QR code on screen. With DeleteMe now taking care of our online privacy, let's head back over to Heidelberg to hear more from Martin on how exactly he's planning to put together this proof.
So usually the natural thing to do is you want to have some kind of quantity that you know you have some a priori knowledge that this quantity, for example, never increases.
Okay.
Right? Like in the case of the Navier-Stokes equations, for example, which we were talking about earlier, that would be the kinetic energy of your fluid.
Yes.
So you know by conservation of energy and so on, if there's no dissipation, the kinetic energy is preserved.
Yep.
And then if there's dissipation, well, it dissipates.
Yep.
But unless you kind of start pushing it or, like pushing it really hard, it's not going to increase. Right?
Yes.
And so you know here a priori that whatever happens, whatever your solution does, you don't have to solve the equation. You know that the kinetic energy is always going to go down. Right?
Yep.
And so now, if you had a good enough solution theory that says, if you start with at some moment in time with some initial data that has finite kinetic energy, then you can continue it a little bit further. If you had a statement like this, well, then it necessarily means that you could extend your solution forever, because you know a priori that whenever you are, your L2 normal, your kinetic energy is going to be less than what it was at the beginning.
Yep.
And in the case of Navier-Stokes, that works in dimension 2, and it does not work in dimension 3, and that's why having global solutions for Navier-Stokes in 3 dimensions is $1 million problem.
And this is very similar, but in 4, potentially.
So this is very similar, right? So in 4 dimension, okay, the Young-Mills equations, they have other problems in 4 dimensions. So the problems they have in 4 dimensions are not quite the same as the problems Navier-Stokes has in 3 dimensions. So it's a different kind of problem. It's in some sense, it's really a different kind of problem. But in principle, these Young-Mills equation in 3 dimensions, which is what we are interested in at the moment, which is a somewhat easier case.
Yes.
They, in principle, from that respect, are supposed to behave somewhat nicely. So there is a quantity which decreases, and it is good enough so that if you have bounds on it, you can restart at least the deterministic form of these equations short times. But the problem is that to build this quantum field theory, you have to look at a stochastic form of these equations. And these are so badly behaved that quantity, like the analog of the kinetic energy, but for Young-Mills, is actually always infinite. It's just always infinite at every moment in time. And so then it's harder to use that in order to actually control anything. Right? And so what we're interested in now is trying to understand mechanisms to go around that in some simpler models. And when I say we, it's not just me and my collaborators, it's also a number of people around in sort of that orbit that have been also thinking about these kind of problems and have obtained sort of some results in that direction.
So with you mentioning this potentially analogous quantity that is infinite, the angular situation, so does that tie into your lecture this morning where you talked about taming infinities?
Yeah, so...
Okay,
so there's infinities popping up pretty much all over the place.
Yeah.
So there's some infinities that already show up just to build this stochastic Young-Mills dynamic. So the solutions are not actually functions of space. They're only what's called distributions, some kind of generalized functions that can have sort of extremely wild oscillations. They're so wild that they're not functions anymore. And then these things, you can't really multiply them, but the equation has products of them in it. And so the interpretation of the equation is very delicate, right? And so there's a lot of infinities that show up if you interpret it in a naive way, and then you have to interpret that correctly. And the equation has a lot of symmetries that help you in that interpretation. So what we showed is that there's only one correct interpretation that really preserves all the symmetries that the equation is supposed to have. And now, if you looked at this energy, well, itself, it's infinite at every moment of time. You could try to think about some kind of renormalized form of that energy, but even that we don't really know how to give a meaning of it, right? So it's worse behaved than the equation itself, and so we don't really know how to give a meaning to a renormalized energy, and so we have to sort of go a little bit try to do something like this. We don't quite manage to do it, and so we're looking at kind of simpler models where you can do something like this, and at least you can, start building techniques that give you some intuition of, how these equations behave, and then hopefully then build towards the Young-Mills in 3D that we're really interested in.
So when you're saying simpler cases, you as you said yourself, we were talking a bit earlier about Navier-Stokes. So you said with one of your PhD students, you'd looked at the 2D case?
Yeah, that's right.
Would that be one of those simpler cases?
Exactly, so that would be one of those simpler cases, would be the Navier-Stokes equations in 2 dimensions.
Yeah.
But so where, in principle, there's no problem getting global solutions because the kinetic energy is good enough to control the equation. But you put a random force that is so strong and that sort of pulls it apart so strongly in different directions that the kinetic energy is actually always infinite. Right? So the kinetic energy is infinite at every moment of time, but then still you want to show that you can somehow control the solution anyway, and it doesn't blow up in finite time.
I see.
And so so that we have a kind of recent result in that direction with a PhD student of mine, which is not yet on the arXiv.
Okay, soon to be available. Yeah.
Hopefully, if no more bug shows up.
And so then, would I be correct in saying by studying these? I love the fact that Navier-Stokes is simpler.
It's 2D.
By studying these simpler situations, again, if I've understood correctly, you're saying you can learn intuition, you can learn techniques, which you then hope will feed into the 3D case of dealing with these infinities. Okay, awesome. And did you show me some potential simulations of Navier-Stokes related things?
I showed you some simulation of Navier-Stokes, which is that one. So it's actually not my simulation. It was done by Sam Punch-Smith, who's a collaborator of mine. So here, that's a simulation of stochastic 2D Navier-Stokes. So vorticity on the left, and that's sort of a linearization of the solution on the right. But that's somewhat it's related to a different problem we're working on. I mean, like here, the random forcing is actually quite regular. So you see that the solutions are, I mean, they become.
It looks like turbulence.
They become
like
pretty
rotating
turbulent.
turbulence.
They become pretty turbulent.
Yeah.
But they're still relatively regular. I mean, here they are not super regular because the viscosity is pretty small.
Okay.
And so you do have actually features at pretty small scales.
Yeah.
But then below that scale, it's really actually smooth. Right? So this is a slightly different kind of situation, and it's what we're interested in here is actually a slightly different question.
What's the question? I'm intrigued now. You've piqued my curiosity. Anything Navier-Stokes and fluids, I'm like, I recognize this kind of figure, right? Red and blue vorticity figures. That's what I see.
So the question here is whether the linearized Navier-Stokes equation actually could possibly decay faster than exponentially, or if it's limited to exponential decay.
Okay.
And this is not actually obvious, and if you write down the linearized equation, there's somehow it could get, right, in principle, the larger at smaller scales, things dissipate faster because of the Laplacian and the dissipation term.
Yep.
And well, as you see in the simulations here, the dynamic produces small scales in the linearized equation, right? And so you might think, well, maybe there's more and more small scales that are produced, and they dissipate actually very fast. And so maybe the linearized equation actually dissipates arbitrarily fast, like at infinite rate, meaning faster than any exponential. But what you can show is that it doesn't. Right?
Right.
So that's
I just love the fact that whilst I think you said yourself, you're not necessarily trying to solve the 2 millennium problems, Navier-Stokes Yang-Mills. I just love the fact that your work leads you to working on these two very famous named equations and series of problems. To me, that's fascinating that you can actually, one person can be working on something and a series of techniques and approaches that could span two of these big problems. Whether it's not exactly the problem itself, I just love the fact that it's also interconnected. Yeah.
But of course, actually the structure of these equations is really quite similar. I mean, if you look at them written out, they are not that different.
Okay.
But then, I mean, each of them has its own, particularities.
Yeah, and actually, I wanted to come back to that. So you mentioned the 4-dimensional case, and you said there's something. I guess my question is, why is 4 dimensions so much? Like, why does that feel like it's the hardest dimension in any problem? Almost, is there something special about 4?
There's something somewhat special about 4 in these type of problems, which is that, at least for quite a large class of these PDEs, 4 dimensions is the one where the strength of the nonlinear effect just balances out with the strength of somehow the Laplacian part and the noisy part.
Okay.
And then, you cannot, like below 4 dimensions, at very, very small scales, the equations look linear.
Yeah,
in a way.
yeah, of course. Right. Yeah.
And actually, at 4 dimensions, the two effects just balance up.
I see. And then as you go higher...
And then as you go higher, it's worse. But then it's sort of, in higher dimensions, then it tends to, it sort of flips, and then it can be, depending on the equation, it can become, again, easier, or at least, but in the sense that things just behave badly, and you kind of know in which way it behaves badly. It might be difficult to show, but at least the intuition becomes again clearer of what happens in higher dimension. And 4 is really the critical one, where in some sense all the effects balance out and they are sort of similar strength at every scale.
I'm really glad I asked you that, because I have, the amount of times I've been reading about a problem and it's always the 4-dimensional case that's the hard one. And I've never understood it. And I feel like I now have a good grasp of like, that was awesome, brilliant, yeah. Now before I let you go, No, I should say, obviously Martin has agreed to be here, but it sounds like I've captured him. No, before you head off to the rest of the sessions today, I know you always have incredible visualizations, and we've seen some of them. I know there are more. So whilst I am aware not all of these will be completely relevant to perhaps what we've been discussing, I would feel bad if I didn't take the opportunity for myself and for the viewers. Can we please look at some of your amazing visualizations of these problems? So this one you said is kind of relevant to young mills.
It is kind of relevant in the sense that, so it's not a visualization of the Young-Mills equations, but it's a different equation in 2 dimensions, but which has a very similar behavior. And what you see here is, well, you see it's a random field, and the 2 dimensions are the screen. The value of the field is the color.
Yep.
Sort of large values are yellow, large negative values are black. And you see that, wherever you look, the colors fluctuate very, very quickly. And even if you zoom in, you would sort of see tiny specks of black inside the yellow, and then even tinier specks of yellow inside the black, and so on. And so you kind of already get a feel from that this is not actually, if you had like the idealized version of this picture, I mean, here, of course, it is a function because there's just finite number of pixels on the screen, and there's one color for every pixel, right? But the actual idealized field that this is supposed to approximate, that one would not be a random function, right? So because at every scale it sort of fluctuates more and more, and the fluctuations are higher and higher the smaller you look, right? And so that maybe gives you a little bit of a feel of how the solutions to these kind of equations behave.
Yeah, and you've just reminded me of a question I meant to ask earlier. So so a lot of your work has focused on stochastic PDEs and bringing in this kind of probability element. So is the reason you've kind of found your way to Yang-Mills and quantum fields, is it because of the probabilistic nature of quantum?
So there's the probabilistic nature of quantum it's not quite the same as the probabilistic nature of these fields. So somehow the link between these fields and actual quantum field theory is, somewhat indirect and technical. So you can build a quantum field theory out of these random fields, but the fact that these are random fields is only sort of incidental to the fact that quantum mechanics is also sort of inherently random.
Yes, okay.
So it's really a different random.
Okay. I have learned there is more than one type of random. Okay, awesome. And are there any other awesome videos? Any other videos that would be relevant? Or have we exhausted your supply at this point?
I think we're kind of running out of supply.
Okay, we're running out. Okay, in that case, can I request that we do Tetris? For old time's sake, can we run my favorite?
I could try to find it.
So the idea is you have a potentially infinitely wide game of Tetris, and the bricks
just
appear in a
fall
random
down.
place and fall vertically down.
Yeah.
And the
then
shape
they
is
just
also
pile
random.
up. And the shape is exactly the Tetris brick shapes. Right? So if I pause this and you kind of zoom in somewhere, I mean, here you really see that's the 5 or 6, I don't know how many different.
And so they are just
sort of snake shape and the L shape and the straight shape and the square shape, and they just pile up.
So then how do you select which shape is appearing?
Oh, just random. Yeah, so I just put them uniformly at random.
Okay,
yeah.
and I guess the position they appear is the same.
Is also uniformly at random, right?
Okay.
Yeah.
And then when we zoom out, it creates.
And then when you zoom out, well, you see that. So here you see the individual bricks, but then you start zooming out, you don't really see the individual bricks anymore, and they fall down like really, really fast.
Yeah.
And you see so you have that random interface, which is kind of the top of your pile of bricks.
It's literally a piece of art. I'm so glad I got to do this again. It's so cool. You need to make this you could sell this to people. Right? Petition in the comments to be like, Martin, can you please, we will all buy this. Make this I could just have so much fun playing around with the patterns this creates. Okay, right. And on that beautiful note, thank you so much as always for having a chat.
Very welcome.
I genuinely, I don't know how many of my other guests are watching this. Probably none of them. I learn so much talking to you every time, so it is a real pleasure. So thank you so much, Martin.
It was a pleasure.
Yeah. And thank you, as always, to all of you for watching the video. If you'd like to see more, this is one of many videos that I'm recording here at the Heidelberg Laureate Forum with other laureates in maths and computer science, so check those out. And if in general you feel like you might be interested in the videos and the content I produce, then please do subscribe, so then you'll get updated every time I release a video. But again, Martin, thank you. Thank you for watching, and I'll see you all very soon.